Polarization and intermolecular forces. A molecule is polar if one side of the molecule carries a charge that isn't balanced out, so the charge is arranged unevenly throughout the molecule, with one side being delta positive and the other side being delta negative. They often have an unbalanced distribution of electrons and are asymmetrical. Water is an example of a polar molecule. The hydrogen atoms are delta positive and the oxygen is delta negative. Water molecules are attracted to one another and other polar molecules as a result of this. Sulfur dioxide is another example of a polar molecule. There is a difference in electronegativity between sulfur and oxygen. The molecule contains two lone pairs of electrons, creating an imbalance in the electronic distribution. At any particular moment, the electrons in an atom may be asymmetrically distributed around the atom, so the atom will have a temporary dipole. The dipole causes electrons in another atom to be attracted or repelled, creating another temporary dipole. These temporary dipoles are constantly being created and destroyed as electrons are always moving. However, the overall effect is that atoms are attracted to one another. A permanent dipole-dipole force, however, exists between permanently polar molecules, so between the delta positive and delta negative ends of two different permanently polar molecules. Hydrogen chloride is an example of a compound that has a permanent dipole. The hydrogen atom has a partially positive charge and the chlorine has a partially negative charge. So these are attracted to one another and a bond is created when they're brought close enough together. Hydrogen fluoride is another example of a compound like this where it has a permanent dipole and it works in the same way. The strongest intermolecular force in water is its hydrogen bonds. A hydrogen bond is produced by the attraction between the water molecules. It makes water cohesive, which means it can travel up the xylem in plants and can also be poured. There are permanent dipole forces in water since water is a polar molecule. The hydrogen ends of the water molecule are delta positive, the oxygen ends are delta negative, creating the dipole. In order of decreasing strength, the types of intermolecular bonds in water are hydrogen bonds, which are the strongest type of intermolecular force. They can occur with fluorine, oxygen and nitrogen. Since they're so strong, substances with hydrogen bonds often have high melting and boiling points. The next strongest are the permanent dipole-dipole forces, where molecules are polar and delta negative and delta positive ends attract each other. And then the weakest kind is the temporary dipole-dipole forces, or the van der Waals forces. In ice, each water molecule makes 4 hydrogen bonds. Each water molecule in general has the ability to create 4 hydrogen bonds, but in liquid water it only makes an average of 3.4 hydrogen bonds. As liquid water cools to form ice, molecules arrange themselves in a lattice tetrahedral structure, so they're held further apart on average than in liquid water. This is an incredibly important property of water as it allows ice to float on the surface of water. Sea creatures are able to survive underneath when things like ponds freeze over. Water also has a very high specific heat capacity. 4.186 joules of energy is required to heat a gram of water by 1 degree. This high specific heat capacity allows water to be a very stable temperature, which makes it a stable environment for fish and other sea creatures to survive in. The high specific heat capacity is also related to water's multiple hydrogen bonds, since these bonds take a lot of energy to break. Water has a high heat of vaporization, meaning a high amount of energy is required to convert 1 gram of liquid water into a gas at a constant temperature. Evaporative cooling is the process by which water molecules evaporate while cooling the surface from which they do so. So because water evaporating takes so much energy, it cools down the surface, which is why we cool down when we sweat. The specific heat capacity of water is linked to its high melting and boiling points. The boiling point of water is 100 degrees Celsius and the melting point of ice is 0. Atomic weights of elements can be determined using the periodic table. Hydrogen has an atomic weight of 1 while oxygen's is 16, which means the molecular weight of water is 18 grams per mole. In the absence of other molecular forces, it would typically be that the higher the mass, the higher the melting and boiling points. However, water has a high melting and boiling point due to the hydrogen bonds and intermolecular forces previously mentioned, despite having a relatively low molar mass.